So hello, everyone. Welcome to episode 2 of the ML4Patents.com webinar series. Before we begin the formal presentations, I'd like to take you through some of the features of the webinar. I know many of you have used GoToWebinar before, but for those of you who are new, all participants, as you just heard, are muted on entry to the call. If you have a problem with any of the technical aspects, please use the questions field on the side of your screen, and we'll try to help you with those as quickly as possible. We'd also like to encourage you to ask the presenters questions at any point. You don't need to wait till the end. To do so, please use the same question field at the side of the screen. Please feel free to use this throughout the webinar, and certain questions we'll try and get to in context right at that moment. Others we might save until the end. And we'll, of course, be in touch with regards to the recording. And you will see here under the handouts, closer to the bottom of the webinar control panel, you can see there are 3 handouts that are available. And please feel free to download those at any point. Okay, so hello again. Welcome to episode 2. This episode features Cipher. And my name is Tony Trippi. I'm the founder of ML4Patents.com and managing director of Patent Informatics. And I'm joined today by Nigel Schweischer and Steve Harris from Cipher. And with that, I will go ahead and turn it over to Nigel to get us started.
Look, thank you, Tony, and a particular thank you to ML4Patents for hosting this series. It's a phenomenal initiative, and I hope that people who join this episode will also listen to the Relativity Patents episode and the ones to come. I think the really understanding ML machine learning in context is really broadening the agenda, and when people understand machine learning, I think all boats float. In terms of introductions, as Tony said, I'm Nigel Schweitzer. My background is as an IP attorney for 25 years, but 8 years ago, Steve and I set up Cipher as a strategic patent intelligence company. And so there's no confusion about who is who. Steve, do you want to say a quick hello?
Hi, I'm Steve. I'm actually a computer scientist by background. I was a researcher at a university in the UK for a number of years, and then founded another startup using ML technologies, but in a different industry.
So Tony, all technical questions to Steve, please. One of the things we did, and we really liked in the last episode of this series, was that everyone was encouraged to continue the conversation. And in that spirit of transparency and openness, if anyone has any questions for either Steve or me after this discussion, please feel free to contact us. Our email is on the slide. One of the things that I really enjoyed about working with Tony and following the patent informatics story, and again the ML4Patents story, is this linear law of patent analysis, which features on several of Tony's blogs. And it's that you don't need a tool. You need to start with why. You need to solve a problem. And many of the products and the technologies and the algorithms which are going to be discussed in this series have all been designed to solve a particular problem. So you can see Tony's linear law of patent analysis. If I had any argument with it at all, it's that the highlighted number 2, the understand the business need and the need behind the need, would be our number 1. In everything that Cipher has done and will continue to do, we always start with why, with no shame in copying the graphic from Simon Sinek's book by the same title. So we're going to eat our own dog food. We're going to follow that progression in this discussion. We're going to start with why. We'll talk about the how. Obviously, Steve, well qualified to talk about how Cipher goes about classifying patents to technologies. But we are also going to end with a demonstration to show what you end up with if you take our why and you follow our how. So this is our why. This is actually our mission statement from our internal statement of our mission, which is to unleash the strategic value of patents. The key word there is strategy, and there's our mission statement. We enable patent owners to make rational decisions, sometimes called evidence-based decisions, by providing strategic patent intelligence powered by machine learning. And I really like that quote from Jared Engstrom when he was working at Red Hat, which obviously Cipher fulfills a need to provide the data, but I love the expression almost magically, using a lens that aligns with Red Hat's view of the world. And it's the almost magically. I think when users are using a tool they trust, when they're getting data which answers their problem, I think gone are the problems of asking how it did it. You know, was it Boolean, or was it NLP, or was it ML? What you've got to end up with is data that can be used easily in the hands of the owners. We talk about strategic patent intelligence, and we claim some credit for having created that as a product category. So what do we mean when we say strategic patent intelligence? Well, I think it's trying to differentiate. It is differentiating from various other activities which Cipher doesn't work in at all, like freedom to operate or patentability. Of course, we're looking to add efficiency, and that might be common to many solutions, but our core technology is to automate the mapping of patents to technologies. And it's also this idea of repeatable results. That's where Cipher really comes into its own. You know, one search, which is particularly intricate and particularly calibrated by the business, Cipher may not be that product to answer that need. But where you want objective, repeatable results for strategic decisions, then Cipher comes into its own. So I keep on saying strategy, strategy, strategy. So is strategy important? We conducted a survey with IAM magazine in March 2020, and March 2021, and we asked a series of questions, all trying to figure out how data was being deployed within an organization. I particularly like this answer because it gives you some kind of framework to understand what are the strategic use cases. One of them is patent strategy, the core idea of building a portfolio which is the right size. But there's many others: competitive intelligence, managing your budget so you can go and prune, or you can do competitive intelligence for corporate comparison or core benchmarking, pruning, quality assurance. But you need the data, and there's that increased demand for data that drives everything that Cipher does. So there's been data around for, I don't know, 40 years. So what's different about Cipher's approach? Well, we've listened to the market, and the data you require is data at the technology level. And I think there's size level, the portfolio size level, which is somewhat trivial and is now available as a commodity. But getting to this technology level is hard, and 75% of patent owners talk about needing that as their core level of analysis. So, okay, if we know that patent strategy is a thing, and we know the technology level analysis is important, what's standing in the way? So in answer to that question, the survey revealed that over half of the audience, the patent owners who responded, said it was too expensive or time consuming, and that just under half said there was no objective or reliable data. And then you can see the other responses. Now, you can see on the left-hand side that benchmarking, as an example, is conducted at least once a year, with many organizations doing it twice, 3 or 4 times a year. So you've got that repeatability, which is why Cipher is well suited for the reasons we explain. And at this point, against that backdrop, this article, which seems to be somewhat of the test that everyone joining the series is having to answer, this is the work that we did with Tony in 2019 and published in World Patent Information in 2020. And at that point, Steve, if I can hand over to you.
Yeah, so
Steve,
as Nigel said, oh, sorry.
Sorry, Steve, just one moment. This handout for this particular paper is part of the handouts. So everybody can get a chance to grab a copy of this. And Nigel, I just wanted to say really very briefly, thank you for that introduction and putting it into the right business context, because that is just so absolutely critical to do a really solid job. Actionable intelligence only comes from a keen business focus and being able to align the output with the objectives of the company. And to hear you talk about it so eloquently and to supply data from that survey, I think just really sends that home. I mean, that just really hammers that point across. And so thank you for that introduction. Steve, please. Sorry for interrupting.
That's good. Yeah, so as Nigel said, this is the work that we did with Tony. It's worth saying that actually the motivation for us was primarily for internal use. So we wanted a data set which had been curated by an expert so that we were sure that the data in there was accurate and it was unbiased, and there's a whole bunch of other characteristics which are all described in the paper. And I'll talk a little bit later about how hard it is to do these test sets. We wanted it to be completely neutral. So during the building of this test set, Tony didn't have access to Cipher, and we put a number of checks in place to make sure that there was no bias in the data set that would make it a particularly easy challenge. But our objective was really to have a neutral test set that we had access to, which would allow us to test future algorithms, because we have obviously a huge number of training sets that we've built using different versions of Cipher, but it's very difficult to use those to test new algorithms because there's a certain bias in those training sets towards the individual algorithms. So it's very difficult to find a new algorithm which might be technologically superior, but it will give worse results because the data you're testing it against is not specialized to that particular technology. So this data set, because it was built without any kind of deep learning technology involved, it doesn't have any of those biases in it, and it's relatively free. And we just relatively free of sort of skew and other sort of problems that can be caused by data. And we decided we might as well release it to the world as a useful resource, as we wanted to publish a paper about the methodology anyway to help other people generate test sets. And we since went on to do one more about cannabinoids, which is also available from the same website where the data is stored. So this is about the conventional way that classifiers are measured. The two most commonly used metrics are precision and recall. Now those are, so precision is a way of saying of the results that were returned by the classifier, what proportion of them are correct. And recall is saying of all the results in the data set that it should have been found, what proportion were found. So in this example, we've got 0.969 precision, which means that in this case, all but 3 of the positives returned by the classifier were actually genuinely positive, true positives. And from the negatives, there were 4 false positives in the negative set, and that gives you these 2 characteristics. There are lots of other different ways of measuring classifiers, and I'll talk a bit about some other ones later. But these 2 happen to be the most common, and they also happen to be the most appropriate for this particular challenge of classifying patents, because there are some interesting characteristics of patent classification which aren't true of many other domains. Mainly, it's the split between the number of positives and negatives. So typically, if there is such a thing as typically, when you're classifying things, there's usually an even number of positives and negatives. But typically in the patent world, that's not true. It's more of a needle in a haystack search. And that causes a huge number of challenges when you're trying to do the classification work, and also means that some of the some other relatively common metrics for measuring the quality of classifiers just aren't useful or don't apply. So yeah, this is showing the 2 factors, precision and recall. That diagram on the left there is illustrating what a test set looks like. So you've got a number of labeled examples. In this case, each of the squares represents a patent family. The green ones are positive, the blue ones are negatives, and the classifiers return the rectangle at the top as being positive, and is predicted rather, the rectangle top positive, and the rectangle at the bottom is negative. And the ones where you can see, if you're not blue-green colorblind, the ones where you can see a crossover are the false positives and the false negatives, respectively. So a false positive is where the patent is in fact negative, but the classifiers identified it as being positive, and the false negatives the inverse. And then there's also a single rolled up metric that you'll see quite commonly called F1, which is it's the average of the precision and recall in actuality, but it's a very specific kind of average. But it's just a way of summing it up in one go. It causes all kinds of problems, but sometimes you need a single number to boil it down to, like if you're trying to choose between two algorithms. So it's occasionally useful, but it can mask a number of underlying problems. So the first thing to say is it's a huge amount of work to build a test set that meets the criteria of being a gold standard, which is pretty much what you need in order to do that kind of precision and recall testing. So you saw from that example that a really small number of misclassified families had caused the scores to go down, and any inclusion of errors in the test set makes the results meaningless, because not only will you get lower scores where the classifier is incorrectly classified, you're also using bits of that gold standard to train on. So if there's errors in your training and errors in your test, then really any scores you get back aren't at all useful or even meaningful. So it's incredibly critical that the test set for this kind of gold standard testing is as good as it can be, and it's been gone over very carefully, and each individual family is being looked at and carefully selected, because just literally one or two patents being mislabeled in the test set will completely skew the results. And we quite often hear of people trying to do this kind of gold standard testing using data that they already had. And, oh, I've got a bunch of patents that came out of my LiDAR department, so they're all about LiDAR. Well, almost certainly they're not. And when we've gone through them by hand, we've typically found lots and lots of errors in there or mislabeled patents. And trying to use that for testing isn't helpful. But on the flip side, this kind of binary classification testing, synthetic testing, it's really only for testing algorithms. It's not actually a particularly, having pulled this work into it sounds a ridiculous thing to say, but it's not actually a particularly good way of saying whether the algorithm will work for you. Particularly pattern classification, it's all about the gray areas. So if you're trying to classify patterns into LiDAR and not LiDAR, it's kind of, the actual straight up and down LiDAR patents are very, very easy. The ones that are only about LiDAR components and they just only mention LiDAR and whatever application you've got in mind. But the reality is the vast majority will be somewhere on the edge. There'll be patents talking about particular components, or there'll be things which apply to LiDAR, or maybe they're a slightly different kind of LiDAR from the one you're interested in. Maybe it's lenses or motors, it could be anything. And only you know what it is you want to include in that test and how much control you want over that gray area and what kind of things you want to see. So really the best test for your particular use case is to try it for real in your use case. You'll never get a sense of how it actually is to use from a synthetic test. The last fallacy that we hear quite often is people saying things like, this classifier has 0.9 precision or 0.9 recall. It just doesn't really mean anything. The measurement of precision and recall is only done with reference to a test set. So you can say, this classifier has 0.9 precision against this test set, but it will have a completely different score against a different test set. And it's not sort of like an absolute thing. You can say, oh, it's got 0.9 precision against this test, so if I run it, I'll see 10% errors. It really depends how difficult the test is. The qubit test that Tony constructed is really quite difficult. So your experience of using that in the real world to classify a quantum computing company, you would see way less errors than you would suggest from the numbers that are coming out of this study. But because we're only testing it over those finite examples, some of which are very, very close, and we were not including anything which is miles and miles away, the apples and astronauts example that Tony's fond of, you get a sort of different impression of what it's like. But as I say, the key test of any ML technology, and particularly classification, is how does it work for me, not how does it do against synthetic benchmarks. And then with that said, I'm now going to talk a lot about synthetic benchmarks. This is about the process of training and using a classifier. So the top half of this diagram is describing the process of training. So the classifier technology itself, out of the box, doesn't know anything at all about your domain. So what you do is you feed it training examples labeled as positive and negative, and you go around an evaluation cycle, which I'll talk more about later, until it's producing results that you like. And then once it's trained, you can then promote it into production. So that phase is called inference, when you're running it over real world data that's never seen before, and using the results. So for our particular use case, as Nigel said earlier, one of the key things is stability and consistency of results. So we have this very clear two-phase approach where you're either training it or you're using it. And when you're using it, the results aren't changing, you're just using it. So you can run reports from quarter to quarter and get consistent results. Sometimes the trainer and the user are the same person, sometimes they're not. But the trainer has to have a degree of domain knowledge, and we've got a specialized UI that we've built that helps you train classifiers, and that does all kinds of things for you. Like, it suggests patterns you might want to look at. It allows you to run evaluations and run various kinds of testing on the current state of the classifier and decide when it's ready for use.
Let me jump in here for just 1 second. As you're talking about all this, I'm just really excited to hear about you talking about this level of detail, because in one of Nigel's early slides, there was this discussion of magic, okay? And what you're telling everybody is very clear that no, really, there's not any magic at all. Nigel said the same thing, but the idea that there is some effort that goes in, it's just like anything else. Any other type of tool, any other endeavor requires effort, it requires skill, it requires patience and time. And as more investment is made, the better the outcomes are going to be. And that's one of the things I appreciate the most about Cipher, is that ability to put additional effort, additional training, work with the model, get it to the point where after a certain amount of due diligence, as you would say, you've got something that's really quite powerful. But that doesn't come without some type of effort. And for people to understand that going in, I think does a great job of setting the expectations to what they ought to be. So thank you for that, Steve. I'll let you continue.
Yeah, and in terms of that effort, I mean, you can get sort of okay results in a couple of hours, but really to produce a classifier that's giving results as good as a domain expert, you're talking 1 to 2 days of effort to train a classifier. So it's really quite a significant amount of work, but it's kind of like you can think of it like an intellectual effort multiplier. You can invest 1 to 2 days of effort in the classifier, but now you've got your domain knowledge, your expertise embodied in this piece of software, and you can then run it over millions of patents in minutes and get results back, which you could never do. There's no expert on the planet that could read tens of millions of patents to find all the ones that relate to a particular topic. But reading 1,000 and labeling those and going around the training loop a few times till it's giving results that you like, that's absolutely a possible thing. So it gives this capability of, I mean, theoretically, there's no reason why you couldn't do this work with an army of people, but you're never going to find an army of experts to read millions of patents, and you would never, even if you could, you'd never get the level of agreement that you want. It's really your ability to embed your knowledge of your company and how you think about technologies into the classifiers that makes it really powerful. And this is, so when we talk about these precision and recall tests, what we're measuring is the ability of the classifier to do that work that we just talked about, of like capturing the knowledge that's fed into it. We're not testing the training process, because that part is, I said 90% human there, it's 99% human. The selection of the training set is it's beyond critical. It's everything. That is what drives the classification. But that part isn't testable. When we run these tests, we typically repeat them kind of 100-200 times, and no one's got the amount of time it takes to do that training process, and it just isn't repeatable in the same way. You know, you can't tweak an algorithm and then run it another 200 times. So what we're trying to do is take the human out of the loop. We kind of virtualize the human in the training process and just test the algorithm. And we're trying to measure how accurate is the algorithm in this synthetic environment where it's been trained on data and tested on data that's all been carefully gone over by Tony to ensure that it's on the right topic. So all of these results you see are kind of glossing over the training process. We do simulate it to a degree, so it's not we're not ignoring that process, but there's no humans involved. It's just testing the algorithm. So this is showing the results we got from running the test in the paper. And actually, we've got a newer generation of the algorithm. This is the data from the paper. We've got a newer generation of the algorithm, which we haven't had time to evaluate yet, because even the evaluation is quite time-consuming. This is showing the same data, just the left-hand chart is zero-based, so it goes down to 0 on the y-axis, and the right-hand chart starts at 0.75, just so that you can see the detail of what happens as the training set size increases. I have a particular dislike of non-zero-based charts, but in this case, you just can't really see anything in the left-hand one. So you can see, so the training set starts out at 50 positives and 50 negatives chosen randomly from the test set, and then we test it on the remaining portion. And you can see at that very small size, the classifier struggles a bit. The recall is very high, but the precision is very low, and that's caused by the fact that selecting, there's a number of reasons, but the key reason is that selecting the negatives is much harder than selecting the positives. And Nigel, could you stop changing the volume because it's covering the screen? As the training set gets larger and we get more and more negatives and they get more representative of the data, the classifier sort of hones in on this even precision and recall, which is typically what we're aiming for. Now, there are scenarios where you want to favor precision over recall for various reasons, or recall over precision. But in this particular situation, we're aiming for a balance. And as you can see, the scores get much higher as it gets towards a larger training set. So around about 300, which is typically 150 positives and 150 negatives, although there's some randomness in there. That's when it starts to sort of level out, and then beyond that, there's no real benefit. And we stop measuring at 350 because beyond there's not enough test sets left to really make the results accurate. When you're running these tests, you divide the data in half and you use one half for training and one half for testing. Obviously, you don't want overlap in there. And at 350, the test set's getting a bit small. So that kind of gives you some idea of the sort of level of accuracy of the algorithm can achieve, and the size of the training set that you need in order to get that level of accuracy. And obviously it varies a bit depending on the domain. For very broad topics, like if you wanted to build a classifier that covered all of quantum computing, so that would be qubits and measurement and all kinds of other technologies, you would likely need a slightly larger training set. And if it was a very large area, like we've trained classifiers that cover clients' entire business units, and those can be like 1,000 positives and 1,000 negatives, just because of the sheer number of technologies you've got to get coverage of. This is an example of two metrics that don't work so well for the patent world. So we've got false discovery rate and false emission rate. Now, false discovery rate is actually just the inverse of precision. But false discovery rate is in the positives referred by the classifier, what proportion of them are actually negative. False emission rate is in the negatives returned by the classifier how many things were omitted. But you can see that there's quite a big skew between these metrics, and the scores for false omission rate are very, very good, but that's caused by the sheer number of negatives in the data set. So this is an example of two that don't work particularly well for patent data. If we move on to the next slide, and this is showing two combined metrics, F1 and accuracy. So I mentioned F1 earlier. That's quite a common way of rolling up precision and recall into a single score. But you can see on the very left there, the numbers are looking okay. You get kind of like 0.83 F1 at a very, very small training set size, but that's masking the fact that precision and recall aren't equal. And in fact, the precision was very, very poor at that stage. You really wouldn't want to use that classifier. But the F1 score, because it's averaging them out, kind of covers that over. And accuracy is not a very useful metric for patents because of this skew between the positives and negatives. The needle in the haystack test. If you've got 1 million families covering some topic and you're trying to discover 1,000 that are on a subtopic in there, if you built a classifier that always said no, it would have 99.9% accuracy, but it wouldn't actually be useful for anything, because accuracy is just a measure of all the results returned, how many were correct, but it doesn't take account of the fact that there might be an imbalance between the positives and negatives, so we don't ever really use it. So this is a little bit about what the training process involves. That's a screenshot of our training system. You effectively review lots of pattern families to determine whether they're relevant to the topic or not, and then mark them. The green rectangles there are families that have been tagged positives, and the regs have been tagged as negatives. And then you go through some training cycles. The next slide's got a bit of a attempt at an illustration of sorry, no, it doesn't. It's one after. So in terms of the data that's used by the classifier system, we use the title and abstract for general background information. We use the claims, which is characterized by the classifier system in a different way to the title and abstract, because the language in there is different and there's some structure and other things which we can use. We use information from the citation network, and we use class codes. I know the class codes are kind of obvious, but they're actually less useful than you might imagine. And we go into some detail in that in the paper about why class codes aren't actually that helpful. I mean, they do help, but they aren't as useful as you might imagine. And there's a few bits of data that we specifically don't use because they cause problems. One is the owner, because we don't want the classifier to be biased towards or against any particular patent holder, because we're typically doing landscaping work. Inventor names for the same reason, because inventors tend to correlate to specific organizations. So training on inventor names causes bias in the results. And also we don't train on non-English text. We just use machine translation to convert it to English and then train on that. And we have a number of tricks for dealing with the wonky translations. So this is the visualization of what the training process looks like. So the red boxes are our proprietary technology, and the dark blue box, obviously the training set, which is the thing that you're building as part of the process. Suggestions analysis are actually two different algorithms, but I've lumped them into one box just because this diagram was complicated enough with them as one. So you start off by, if you have some seed data, sort of high quality labeled data, you can upload that to seed this training set process, or you can just start from scratch and start doing searches and adding positives and negatives. And then it's just a process of going around, adding more labeled data, retraining the classifier, evaluating the results in various different ways. And we provide a lot of tools for that evaluation. You can run your part completed classifier over random patterns. You can run it over particular portfolios of interest. You can run it over CPC codes, all kinds of things. And then we've got these suggestions and analysis processes, which kind of automate the work of making sure that you haven't missed sub-technologies or particular areas of interest, or there aren't related technologies that aren't included in your negatives that you need to exclude. And they go a long way towards speeding up the process to get it as quick as possible. And this user interface that we've built for doing this work, we put a huge amount of effort into it because it's something which we make available to clients, or some clients, but we also use it a lot internally for building our taxonomies and classifiers.
And back to the open offer we said at the start, there'll be those people who are curious about the training process, and there's an open offer for anyone on the call. If you want to be talked through the training process, even down to the level of seeing the classifier builder, we're more than happy to show you that. I mean, I think there's a lot of mystery about, you know, ML, even AI, about it's sort of trying to eliminate humans, but this is a true partnership between the things that machines do well and things that humans do well, and it's trying to go on optimized for both. So that trainer in my head is like, you know, twice as large as that, because you're choosing, as I talk about on this slide, you're choosing the taxonomy. That's absolutely human. You're going to decide what set of technology is organized in what way, with what scope, and then you're going to train to that scope to end up with the outcome. So I don't know whether, Tony, there's any questions coming in on the how part, or whether I should go and risk my life.
2 of them.
Yeah.
There's 2 of them, so let me ask them quickly. First one is Cipher a patent database with machine learning, or only a standalone machine learning / analytics tool?
Yeah, it's a pattern database with machine learning on top, and we have you know, all the tools you would expect to see inside a patent database, although it's very much specialized towards the kind of work that we do around landscaping and strategic data and comparing companies and so on. But obviously we need to have all that data in order to run the training process. One thing that's worth saying is we do only classify patents. So the reason we can get those very, very high levels of accuracy is because Cipher does not do, you know, product literature or invention disclosure or anything else. It's patents and patents only. We train on patents, we run on patents. And that was a very conscious decision that we took, because we wanted to give the kind of levels of accuracy that the patent experts expect to get. And that is the only techniques currently available that can give that level of accuracy have to be very, very, very domain specific.
So the second question, and I think to a degree this has been addressed, but I'll just go ahead and ask it. So if you're not using qubits, if you're using, say, something like nanotechnology, there's still this need for some sort of standard, some sort of training set that reaches almost the same or the same level of accuracy as the gold standard does for qubits. Is that correct?
Yes and no. So yes, the training set is obviously critical, but it doesn't need to have quite the same level of accuracy, because the classifier is tolerant to a certain amount of sort of fuzziness in the input. And there's a very big difference. So a gold standard, you need every positive example to be really sort of very distinctly related to the topic, and every negative example to be really very distinctly not related to the topic. Whereas when we're actually building classifiers for clients for real, or they're building them themselves, they're really very interested in the gray areas. So it's how do we define IoT or I forgot what you had, nanotechnology. It's not about how does some remote expert do it. It's like, well, what are we really interested in? Like, do we regard that to be nanotechnology or not? Like, is MEMS included? You know, all of these things. And those are decisions that you get to make, and that's the power of the system. So it's nowhere near as, building a training set is nowhere near as intensive as building a gold standard. And also we had to ensure that that Tony wasn't using any like really high-tech techniques to build the gold standard, because that might have included skew in there. So and obviously our training system has loads of things to help you build it up, which is why you can get a really good training set in a day or 2 days.
Fantastic. We have one other question that came in, but I'm going to save that till the end. So Nigel, you have time to go ahead and show us the product and show us some of the features and some of the taxonomies that you already have.
Yeah, no, I'm more than happy to do that. And I say, because I think the questions have been of such high quality, I think we should allow them to come to the fore. So I really will take this at speed. But these are a couple of the problems we solve, looking at landscaping and benchmarking. And we do it in a couple of different ways. So I'll try and illustrate very quickly both ways. One of which is a global landscape, which I think really shows the joy of Cipher. It doesn't mind running a search across all patents, running the classifiers across all patents. So let's go and show that approach. There are a number of taxonomies. Of course, the taxonomy inside the product for our customers is their definition. This is a real taxonomy. This is the one which Mintel used to publish their patent insight reports, and we have permission to demonstrate it. So I'll do just that. It's split into two fundamental categories, beauty and personal care. And for this search, let's say we go down to skin microbiome. As illustrated on the slide, every classifier, as Steve was stressing over and over, has the customer's very specific boundaries, what it includes and what it excludes. Let's also choose, say, surface disinfection, very popular in COVID. And let's take a couple of food categories, let's say immune health. Let's do a bit of infant formula, a bit of sports nutrition. Let's go and say stop there. So you've got the classifiers that you want to run. We're asking it to run those classifiers against all patents in the world, and you hit that button. You hit that button. It is not quick. Well, sorry, it's quick in terms of human beings reading all patents in the world, trying to go and find all patents relating to those 6 topics. But this report takes about just under 4 hours, about 3 hours 30 to create. Funnily enough, I'm not going to ask you to go and wait that long. There is the report that is returned. It's sent to you by email. You open it up in the system, and that is the all patents in the world relating to those 6 categories: immune health, blah, blah, blah. So you're only looking for 14,000 results out of 100 million documents. So, you know, when Steve draws a neat picture of Tony's training set, which was a relatively balanced set of positive and negatives, you get something which looks rather blue-green, as Steve's slide did. When you're looking at this, it's 14,500 out of as I just said, 100 million. So if you were to go and focus in on, say, one technology, let's go and say it was, which one? Surface disinfection. We look at surface disinfection. Now we want to go and look at the top owners. Once you've got that data set, of course, everything else is real time. So timely for the machine to go and actually spin up and go and search all patents. But once you get the report, you're then instantaneously navigating. In this case, it's showing you the top 15 owners. You could look at all owners clearly, top 15 owners of the particular technology I selected, which was surface disinfection. And you also get this kind of nice view, which I really like this view, which shows that the top 15, in this case, just own more than 52%. But as we all know, the magic is in the long tail. And in this case, the long tail is 47% of the world. I'll stop there on that search. I want to go and just do one other search, because I think it shows you the other view. That takes time because it's searching, running those classifiers across the world, and it's about 45 minutes of machine time per classifier. What happens if I wanted to go and I knew a set of companies and I knew a set of technologies? So let's run that report. Cipher knows all organizations in the world who own patents. It's got a very sophisticated corporate grouping tool. So let's go and see, we want to start with General Motors. General Motors is there. We can select it if you don't really want to go and spend time on corporate grouping today, because this discussion is about classification, but you can see that General Motors owns under a variety of names, including Tula and various other Chinese companies. It owns a bunch of different patents under a bunch of different names. Everything in a system for strategic patent intelligence has to make it easy for the user. The system will suggest to you companies that own similar portfolios, but it doesn't mandate you use those. So you might suggest, oh, well, Ford and GM are an interesting comparison set, but you might also decide to go and include some Japanese OEMs So you can so you can manually enter Toyota. You're then back to machine selected. Oh, it hasn't given me Hyundai. I want to add in Hyundai, and hey presto, you've ended up with a set of, I've clearly spelled Hyundai wrongly, so we'll forget that one for a minute. But on the report I did earlier, I did go on. So you, oh, sorry, yeah. So then you go and select your classifiers. So you go to your taxonomy. This is one of our demonstration automotive one, which made Cipher famous because this was the first taxonomy that we actually launched. It's a nested taxonomy. Autonomous systems is broken down into ADAS components. ADAS components is further broken down. And this is what we mean by humans. The machine did not do this. This was put together by a bunch of automotive experts and some significant collaboration with the industry to say what shape would make sense. And so you can see at the lowest level, the fourth level, you've got a set of sensors. Let's say we're going for all ADAS components. So now we've got the set of companies, we've got the set of technologies. Cipher's going to ask you two further questions. Number one, do you want it to be mutually exclusive? Or number two, do you want it to be overlapping? And that's hugely important. Let's run the search at the moment on mutually exclusive. And it's also going to ask you whether you want to include those things that fall outside the scope of the binary classifiers. Let's say yes to that. If you run that report, this one takes 42 minutes to generate, but still don't have that much time. This is the report that is returned off this. With the correct spelling of, oh, was Hyundai? I thought Hyundai was in there. If I select all, there you go, Hyundai. Oh, it's Hyundie. Apologies for that. Now you've got the technologies, the top, the LiDAR, the radar, and you've got that. Now, much easier this time, because when the reason it's 42 minutes rather than 4 hours is look at the data set we were running against, because it's bounded by the company set. Those classifiers are only being run against 195,000 assets. So let's imagine that Cipher reads 61 million patents an hour. Do the maths. You can see it's a much quicker job to go and classify 195. Again, back to Tony's question about does it have all the analytics, or back to the question from the audience, does it have all the analytics? Yes, it does. So if you wanted to go and focus on, say, just radar, you could go and focus on radar. If you wanted to focus on just, let's take two companies here, Volkswagen and GM, and you look, say you want a geography analysis, then you select the geography chart, and all of a sudden, I'm going to just go to, yeah, so there you've got the geography chart showing you, sorry, technologies. I've got unrelated in, apologies. Unselect. So now I'm just looking at their radar patents. I really didn't think that they had 100,000 radar patents. So now we've got VW on the top line, we've got GM on the second line, broken down in this particular view by region. And then all of a sudden, I mentioned strategy, you get that instantaneous view of what their patent strategy is from a geographic perspective. You can see VW, very home specific, fundamentally makes its primary domain Germany, and General Motors, of course, very US centric, with a very noticeable difference in this technology in their China strategy. So that is what we call stunt demonstration, and I'm going to stop sharing because hopefully I've allowed enough time for questions. So I say anyone who wants a slow motion replay of that, feel free to contact me or Steve, and we can go and talk through either the classifier builder or show the reports. But hopefully that gives you the idea of this kind of repeatable in use. You know, the first one ran its report over 100 million patents 6 times. Second report ran 21 classifiers over 196,000 assets. Difference in speed, but the same ease of use.
So yeah, that's fantastic. And there are a couple of questions. I'm actually really curious. I was happy somebody asked about this because I was thinking something similar. Tell me a little bit about mutually exclusive. Because yeah, that's a big thing. I actually spend a fair amount of time thinking about mutual exclusivity in even some of my own work. So let's hear a little bit more about what that means, and how it's accomplished and why you selected it.
Yeah, so when you're applying, obviously if you're applying a single classifier, there's not really any decision to be made. It's either the patterns are either positive or negative to it, and you get that result. But when you're applying multiple classifiers, depending on your use case, you might want to see either every pattern assigned to the most relevant category, or every pattern assigned to every category that's relevant to. So if you're doing LiDAR and radar, to go back to a previous example, you might have a pattern which relates to both LiDAR and radar, and you want to see that. And if you're doing a licensing program, for example, you would want to see that in both categories. But if you're just trying to say, I'm looking at my competitor and I want to see where they're focusing their effort, you want everything assigned uniquely to one of the categories. So the way it does that is, and in ML jargon, these are called multi-label and multi-class, but the way it does it is by, it runs every family through every classifier, and then it looks at the confidence scores coming out of the classifier, and the class that has the highest confidence score wins that family in mutually exclusive mode. So it's just basically forcing the system to assign it to the one that it thinks it's most likely to be relevant to. But it's an important capability, and I say, like, different use cases lead you to run it in different modes.
And are they in either mode? How is the decision made with regards to the threshold?
So we have there's a threshold of 0.5 for each. That's the threshold that the classifiers are trained to. So you'll get the best results by including in each technology, including every family that scores 0.5 or greater. There are some cases where you want to move that threshold, but that's that same confidence score as the number that we use for designing the mutual exclusivity. But you can actually move that threshold up and down. So I talked a little bit earlier about there are sometimes reasons why you want to favor precision over recall. So for example, if you've been offered a license from someone's portfolio, you want to make sure you capture everything. You want very high recall, and you're not so worried about the precision because you're probably dealing in small numbers and you can filter them out yourself. So in that case, you can drop the threshold in order to see more things that are around the edge, related technologies, but not actually the same way. Similarly, for alerting on new publications, people sometimes do that at a lower threshold. There are actually other ways that you can change the balance, though. You can actually specifically train the classifier to be broad or narrow. If you've got a case where you always want to run this classifier in a sort of very broad, all-encompassing way, you can deliberately train it to include peripheral things, and it will learn to include more than it excludes.
Outstanding. Okay. Another question here that was going back to the training process with regards to the cyclical training process. And I think this is a really great answer because, I mean, I talk about this when I talk about collection development. I've got this sort of hand wavy 90% recall, 70% precision. That speaks to what you were just saying. But the question is, well, how do you know when to stop? And at what point can you say that you're going to be satisfied with the results? So what would be your response with regards to the cyclical training process?
Yeah, so I mean that's the big decision, and it really depends on what you're trying to do with the classifier. But I mean the sort of glib answer is when you're happy with the results is when you should stop. But the reality is that people tend to come back to them. So they'll often do, if they're building a classifier for a particular purpose, like we need to run a landscape on LiDAR technology. So you sort of do some rough build, you run the classifier, you present the results, everyone's very happy. But then later you've got another project where you want a more precise definition, or it's more critical that you get exactly the right data. Then you can go in and jump back in and do some more work on it. And you can fork them and things like that if you want to maintain the original one for whatever reason. So there isn't really an easy answer to that, but we do offer a lot of tools that help you tell where you've reached the point of diminishing returns, because you can always keep adding more data to the training data. It's just at some point, it's just not really worth you spending another 3 or 4 hours on a marginal improvement, because frankly, at the size, it's rarely, you can quite quickly get to the point where you're only dealing in gray areas and you're just kind of scratching your head thinking, would I want that in the training set, or sorry, in the result set or not? And at that point, you're probably done, but there isn't any sort of green flag that comes up and says, yeah, you're done, brilliant, press go. It's a bit more human than that.
And the only thing I'd add to that is this is just a machine. Don't expect the machine to go and do anything that a human can't do. So if you end up with a patent, you go, I've looked at it, I've spent an hour looking at it, and I don't know whether it's in or whether it's out. It's just literally sitting on the fence. It's not like you can show it to Cipher and it will make that decision for you. Cipher can only do what it's been trained to do. So we live in a patent world. There are just murky gray zones, and more of those than we would like.
Yeah, I think it's a great answer. Diminishing returns is really where it's all about. And it's just not worth the extra effort for, especially when you're talking about landscapes and you're talking about trends. Does it really make that big of a difference because you added 2 extra records? I don't see that. That really doesn't sway the overall trends when you get right down to it. Final question. It seems very clear that this system is great for ongoing efforts that we would traditionally call alerts. Okay, so can you talk a little bit about how a company would use Cipher on in your benchmarking? You also talked about the idea, they're right now they're doing this once a year. So the company's going to be able to do this once a week, once a month, and how is the system set up to more efficiently manage that process?
Do you want to kick off, Nigel? And I'll,
okay, it may be kicking off and closing, because I think we'll let you down to the last 2 minutes. But for those people who are paying very close attention, or for those people who want to go to the slow motion replay of the demo, there was a button there called alerts. It's a beautiful thing, because the alert button says which classifiers do I want to go on monitor, and then every frequency to be decided every week, every month, you get patterns which are positive to that classifier. And the beautiful thing is it remembers what you've seen already. So a lot of the systems, a lot of the problems that we were told about when designing that is some systems show you the US one and then show you the Japanese one and then show you, and of course it's only one family. So Cipher's very particularly calibrated towards families, and will show you the new families and enable you to create a report. So if there's 100 new LiDAR patents this month, press a button, it will sort it by owner, sort it by geography, and all of a sudden you can do A, you don't have to go into the system, but B, you're getting that kind of filtered set with that repeatable approach. So Tony, whoever's asked that question has actually totally understood the objectivity and repeatability. They're getting the same question asked in the same way with the same level of accuracy, but also being offered up that moment of reflection to say, am I seeing too much stuff which is wider, which can of course be fed back to the classifier building process to say, is it time to recalibrate because we would like it to be narrowed, or whatever change you want to have made.
Yeah, and the Cipher system is absolutely set up for that kind of repeating report. So you can, the report that Nigel created with the, I don't know, half a dozen companies and 8 or 9 technologies, you can just go on that, click on the report and rerun it with today's data, and you get exactly comparable numbers. The organizational definitions are consistent, the scope of the classifiers is consistent. So you can, and this is really the big win, is you can compare numbers from last month to this month and know that any changes you're seeing, assuming you haven't retrained the classifier, that any changes you're seeing are due to actual changes in the patent system, not just because someone had a different opinion of how to search for LiDAR this month.
Well, gentlemen, I can't thank you enough for your time. I can't thank you enough for your diligence and all the effort you put into this session. It was outstanding. Went through everything that we hope to accomplish. And once again, thank you very, very, very much. We'll have episode 3. The registration page will go up very soon. But again, thank you, and again, greatly appreciated.
Thank you, Tony.
Great, thank you.